My project is on the applications and importance of solids of revolutions in the manufacturing process. First, let's look at the manufacturing process. Manufacturing is the large-scale making of goods or wares by manual labor or by machinery. For large-scale manufacturing to be both efficient and cost-effective, the design process is crucial. Without the ability to create good designs, manufacturing would not be as prominent or effective. Once a design has been created, there are an additional two steps that are centered solely on cost-effective manufacturing. These are design for manufacturability, which is the method of design for ease of manufacturing of the collection of parts that will form the product after assembly, and design for assembly, the method of design of the product for ease of the actual assembly of the products. How are solids of revolutions applicable in DFM, design for manufacturability? This engineering process often requires the use of CAD and/or additional software to create the products which will be forms of solids of revolutions. In CAD, for example, 3D models are created by rotating two-dimensional drawings about a specified axis. This software is made possible because of the theories behind creating irregular solids in calculus. In calculus, regions between functions and lines are rotated about a specified axis for a specified interval, just like the 3D models in CAD are created. The two links are video simulations for the theory of three-dimensional modeling in calculus and creating 3D models using the CAD software. Having the ability to create these three-dimensional models allows the manufacturing to be more efficient. The CAD software and other 3D modeling allows each individual component to be individually analyzed, measured, and changed. This ability gives manufacturers the ability to test stress factors and tolerances of individual parts of the model before production, which helps avoid not only costly errors, but also make the manufacturing process more efficient, which is the goal of the DFM process. Three-dimensional modeling can help to reduce the number of parts, simplify parts, and eliminate unnecessary features of a part or product that makes it challenging to manufacture. For example, it can reduce instances where a radius is unnecessarily small, a surface that is unnecessarily smooth, or tolerances that are unnecessarily high. To see a simulation by SolidWorks on why three-dimensional modeling is so important, check out the link. Once the designs in CAD are created, analyzed, and approved, the CAM software uses the models and assemblies created in the CAD software to generate toolpaths that drive the machines that turn the designs into physical parts. Ultimately, it is because of the ability to create these solids of revolutions that the design for the manufacturing process is as impactful in both the cost and the actual manufacturability of the products. It is clear that the theories behind creating solids of revolutions in calculus are vital in manufacturing in both the actual creation of the products as well as the design for manufacturing process. But how else is calculus applied? The design for assembly process is all about optimizing assembly, which covers many different variables, but we are just going to look at solids of revolutions and their volumes. Whether manufacturers calculate it by hand or use computer software, knowing the volumes of the irregularly shaped products is key to optimizing assembly. As review, how is the volume calculated? To do this, we use the equation volume equals pi times the antiderivative of the function squared for the interval from a to b. In this sample problem, the function is f of x equals 3x, and the interval is x equals 0 to x equals 1. This is because that is where the function intersects with the x-axis, which is what the function is revolving about. From here we get volume equals pi times the antiderivative of 9x squared from 0 to 1. Ultimately, we get volume equals 3 pi units cubed. This problem is very similar to the last problem, but the solid has a section that is hollow. For these types of problems, the volume is equal to pi times the antiderivative of the upper function, which is f of x, squared, minus the lower function, g of x, squared for an interval of x equals a to x equal b for a rotation about the x-axis. In this problem, the upper function is the square root of x, and the lower function is 1/2. The interval is from 1/4 to 4, as seen in the model. Once the equations and values are plugged in, the volume is 22.089 units cubed. Lastly, there is the shell method. Volume is equal to 2 pi times the antiderivative of x times the difference between the outer and inner functions, f of x and g of x, for the interval from a to b. For rotation about the y-axis, the interval is for x equals a and x equals b. For this example, the interval is from x equals 0 to x equals 1, because those are the points where the two functions intersect. Plugging the values and functions into the equation, the volume is equal to 3/10 pi units cubed. By determining the exact volume, manufacturers can determine the exact amount of raw materials needed for each unit of product without having to take measurements from an expensive prototype or by approximating the volume, which ultimately cuts costs. The manufacturers can then determine more easily and with much less error how much material to acquire, making this part of the assembly process much more efficient. From knowing the amount of material, it is a simple conversion to determine cost per unit of product. With more accuracy in the amount of material, businesses can provide more accurate quotes, which helps to win over clients. Both the theories behind creating solids of revolutions, which is what makes 3D modeling possible, and the ability to determine volume, and from this, costs, are major aspects for preparing for manufacturing. These charts show how important these steps are in large-scale manufacturing. From the design, it is a relatively easy conversion into CAM or similar software to actually create the final products on large scale. The applications of solids of revolutions in the manufacturing process show how important calculus is to manufacturing. This shows how calculus is not only used in the hard sciences, but is also extremely important in the everyday world.